In this video, we will be looking at some logarithmic function applications. And we're going to start with an earthquake intensity example. Now, the Richter scale is something that is used to measure the magnitude of an earthquake, and it was a scale that was developed by Charles F. Richter. The formula that is used to calculate the magnitude is the log of, now the base is 10, and the argument is a ratio of the intensity of the earthquake that is being measured to the intensity of a reference or standard earthquake. So let's look at our first example. This one is going to be on the more basic side, and then we'll look at another version. In 1989, a major earthquake hit San Francisco. It was the largest earthquake in that area since 1906. This earthquake was approximately 12,589,254 times more intense than the standard earthquake. What was the magnitude of this earthquake? So the fact that it tells us how much more intense it was, that actually gives us that ratio of the intensity of the earthquake being measured with reference to the intensity of the standard earthquake, which means we're just subbing in the given number for the argument. And it's just a base 10 log, so we just punch this into our calculator and it will give us the magnitude. And if you punch it in, you get a magnitude of 7.1. So therefore, the magnitude was 7.1. Now, like I said, this was a basic one because it did give us that ratio of the intensity. Let's look to a different style. In October of 2005, Pakistan experienced an earthquake of magnitude 7.6, resulting in the death of over 73,000 people. Later on that month, Owen Sound experienced an earthquake of 4.2 in magnitude. How many times more intense was the Pakistan earthquake to the quake in Owen Sound? So here we're talking about intensity, and we want to see how much more intense one earthquake was with reference to the other. So our end goal is to find the intensity of the Pakistan earthquake relative to the intensity of the Owen Sound earthquake. So we want to find whatever this value is. This is going to take us two different calculations. I'm going to do one calculation using the magnitude of the first earthquake and then another for the second. So the earthquake in Pakistan had a magnitude of 7.6, so I'm going to replace m with that, and that is equal to log of the intensity of that earthquake relative to that reference earthquake. And here I want to isolate for the intensity of the Pakistan earthquake. So remember, we have that invisible base 10, so I'm going to just convert this into exponential form. 10 to the power of 7.6 is equal to intensity of P over the intensity of the reference. And then I'll just multiply both sides by the intensity of that reference earthquake. And now I have isolated for the intensity of this specific earthquake. Now I'm going to do the same thing for the Owen Sound earthquake. So its magnitude was 4.2. So 4.2 is equal to the log, I'll just put that little base, of the intensity of the Owen Sound earthquake relative to the reference earthquake. And again, 10 to the power of 4.2 equals that ratio. And now I'll multiply both sides by that reference intensity. And now that I have these isolated expressions for the two intensities, I can sub them in to my end goal. So instead of IP, I'm going to write 10 to the power of 7.6 times the intensity of the reference over 10 to the power of 4.2 over the intensity of the reference earthquake. Those cancel out, and then I'm left with two exponential terms. They have the same base. They're being divided, so we can subtract these exponents so that we have 10 to the power of 3.4. And this would be the exact value. If I sub it into my calculator, I get approximately 2,511.89. So that's how many times more intense the Pakistan earthquake was relative to the Owen Sound one. So I've run out of space here for my therefore statement, so I'm just going to say it out loud. Therefore, the earthquake in Pakistan was 2,511.89 times more intense than the Owen Sound one. And there we are. This one's a little bit more work because we had to do a comparison and an isolation. So the magnitude of an earthquake is one application of logarithms. Another one that is very similar is sound intensity. So the loudness of sound is measured using a logarithmic scale, and the sound loudness is compared to the sound of threshold hearing, and the units that we use are decibels. Our formula is going to be L equals 10 times the log of, and our argument here is going to be the intensity of the sound being measured over the intensity of the sound at the threshold of hearing. So very similar to the earthquake magnitude, it's just that the log is being multiplied by 10 at the end. So here, our first and only question about sound intensity is how much more intense is the sound at a rock concert, which is 123 decibels, compared to a crying baby, which is 80 decibels. So very similar to the previous example, our goal here, we're talking about intensity. So we want to see how much more intense is the rock concert relative to the intensity of a crying baby. So there's our end goal, and it's going to be very similar to what we just did. I'm going to have two separate calculations here for the rock concert and the crying baby. I'm going to isolate for the intensity of the rock concert, the intensity of the crying baby, and then put it all together. So let's get started with that. The loudness for a rock concert was 123 decibels. Unlike the previous example, I can't go straight into exponential form. I'm going to divide both sides by 10 first, so I could get rid of that coefficient. Now, invisible base of 10, so this becomes 10 to the power of 12.3 equals the intensity of the rock concert over the intensity of the sound at the threshold of hearing, and now we'll multiply both sides by that threshold. And I'll keep that to the side, and now I'll do the same thing for the crying baby. The loudness was 80 decibels. Oh, actually I used C for crying. So we'll divide both sides by 10. And here I'm just going to skip ahead. I'm going to convert this into exponential form, so 10 to the power of 8, and I'll multiply it by that denominator just to isolate a little faster. And now I can take these expressions and put them into my end goal. So 10 to the power of 12.3 times threshold intensity over 10 to the 8 times threshold intensity. You'll know you've done this correctly if those intensity of sound at the threshold of hearing cancel out. And now I can subtract my exponents. So 12.3 minus 8 is 4.3. And that's our exact, if I punch it into my calculator, 19,952.62 times more intense. And again, I've kind of run out of space for my therefore statement. So therefore, a rock concert is 19,952.62 times more intense than a crying baby. Okay, so very, very similar. That's why I've only put one example here. Okay. And our final application is a pH scale application. Now the pH scale measures the acidity of substances. If on a pH scale we go from 0 to 14, 7 is considered neutral. Anything less than that is considered as acidic. So the closer to 0 you are, the more acidic. And anything past 7, so between 7 and 14, it's more basic. Okay, and we can calculate the pH of a substance with the following formula. Negative log of, this H plus is the concentration of hydrogen ions in moles per liter. Okay, I'm not going to do much with this, and you could look at that scale to get an idea of, you know, daily substances that you might use, if they're acidic, if they're basic, but I'm going to give you the pH and we're going to calculate the hydrogen ion concentration. So milk has a pH of 6.8, so it's pretty close to neutral, slightly acidic. Let's find that hydrogen ion concentration. So 6.8 is equal to negative log of that concentration. We have to divide both sides by that -1 first. And then we can convert into exponential form. So invisible base there, 10 to the -6.8 is the hydrogen ion concentration. And because I don't really have space for my therefore statement, I'm just going to put my units right underneath here, moles per liter. So therefore, the hydrogen ion concentration of milk is 10 to the power of -6.8 moles per liter. Now, you could keep it like this. You can punch it into your calculator. It's still going to be a very small number, but maybe it's more meaningful if you plug it into your calculator and you get something like 1.58 times 10 to the -7 moles per liter. So just seeing that 1.58 might mean a little bit more. All right, peanut butter has a pH of 6.3. Let's find the hydrogen ion concentration. So very similar here. Divide both sides by that -1. And then go into exponential form. You'll see with all of these applications, it's a lot of swapping back and forth between the forms. Okay, and if you punch this into your calculator, we get approximately 5.01 times 10 to the power of -7 moles per liter. And there we have it, 3 applications related to logarithmic functions.